So still people coming. It's so good that this container topic is probably almost able to fill a room with 600 people. So I'm really excited. So hello, everybody, and welcome to this summit in Switzerland. I hope you like it so far. We had a serverless deep dive just before. We're doing a container deep dive right now, and there will be an advanced networking deep dive later. So welcome. My name is Frank Munz. I'm a technical evangelist working for Amazon Web Services in Munich. And I'll be here on stage later with Brian. Where is he? He's there. He's there. OK. He didn't get lost. And he's going to tell you a little bit more about the customer story. This is a level 300 talk. That means it's like medium difficulty. We assume you know a bit about containers, but we don't assume that you have done an implementation with these services yet. The agenda is very easy. I don't want to make a product feature talk. What I'm trying to do is connecting the dots, talking about architecture, mentioning tools where it's appropriate, and explain you a little bit more about the how and the why. Let's talk about technical details of containers first. That's good to get started. It also helps us to understand services like ECS and EKS that I will talk about later much better. So let's start with the technical underpinnings. If you start a container today and you run a shell in this container, it almost feels like a virtual machine, doesn't it? You see a CPU, you see RAM, you have your own file system, you have an IP address, there is a network stack, you're connected to the internet, and it feels like a VM, but it's not. It's actually a container that is using Linux primitives like control groups, like namespaces, and like this union file system to create this, almost this magic of being a container now. And if we look at those C groups, they define resource limits. They were merged into the Linux kernel in 2008, and the actual implementation is delegated to subsystems. ECS, the Elastic Container Service, is using these C groups to get memory and CPU utilization information about the tasks that you're running. And CAdvisor, and if you know this tool, is doing exactly the same. This C group abstraction is working really well. But there were some tiny issues that we had, like if you're a Java developer, you know this. Java was not respecting those C groups for a long time. So if you were running Java in a container, Java was looking at the whole RAM that you had on the machine and all the cores from your processor on that machine. And then based on the number of processors, it was trying to detect the number of threads it should use for garbage collection, for just-in-time compilation. And it was also trying to set up the heap, and there's a complicated set of rules. But basically what it does, it tries to allocate like 1/4 of the available RAM. But actually, it's seeing the whole RAM and not the C-grouped RAM as you would expect this. And this was fixed in Java 10. So 10, 11, 12, 13, they're all good. And it's backported to 8. So with a modern Java version, you should be OK. But there was some time when this was not working perfectly. If we look at the namespaces, those namespaces are there to partition, to isolate resources. And for every process is assigned to a namespace of each category, but one category could hold more than one process. So it's a good abstraction. But again, you have to know where it breaks, this abstraction. Did you ever try to run an uptime command in a container? So I start a container, you run the uptime command in a container, guess what happens? What will it show? Is the uptime like, does it take a second for the container to spin up and the command will report 1 second or half a second or 10 milliseconds? That's what happens. You see something like 2 days, 2 hours and 57 minutes. Because, again, the container is not getting the uptime from the container, but from the underlying kernel, from the underlying Linux operating system. So you have to know those little glitches to be really successful using container technology. It is a good abstraction, but it's not perfect. Talking about the namespaces and looking at network namespaces, it gets more interesting. If you start a Docker container, every new Docker container gets a new network namespace. So it sees its own IP address, it has its own network stack, and so on. But then we can also have containers that share the same namespace. And this is what happens if you run a Kubernetes pod or an ECS task. They share the same namespace. Later, when I talk about AppMeshes, you will see that this is a core principle of injecting a container to a running pod. And this is how we get those sidecar proxies working. And I'll come back to this in a minute. But this is just how the things are connected from core technology on a container level to what we do with services. And then, of course, the other way to go is that you assign a particular ENI to a task or to a pod to get more separation. The union file system, that's maybe the easiest part to understand, and you have all seen this. If you've ever started a Docker container, a Docker image to run a container where you didn't have the layers from this image locally, what happens is it will be downloaded automatically. So you see this pull, and you see the separate layers being downloaded, and the last layer that is running on top is the writable layer, is the writable layer. So it's there to make efficient use of storage. Now, if you build a container, the question is, how do you build such a container? So we need to talk a little bit about programming languages and frameworks, and it all starts with this Dockerfile, doesn't it? You all seen a Dockerfile, and typically on the first line you see something from CentOS 7, from Ubuntu, from Alpine. And the question is, why do we do that? Well, there's a couple of answers. First of all, I think we should understand that this image that we build is not containing a Linux kernel. So the container that is running at the end is a C group restricted, namespace isolated process that is running on the Linux host, but there is no kernel in this image. And still we say from Ubuntu, from CentOS 7, from Amazon Linux, whatever. And why are we doing that? The answer is because we need all these little tools like apt-key and rm-rf and so on. If we wouldn't include the Linux, we wouldn't have those tools. The answer is we don't know any better, no? It's hard to restrict what we really need in such a container. And this is one of the reasons why people are so happy with Go. Like, if you use a modern language like Go, what you can do is what your parents did in the 80s with C and C++ when they did a static binary, when they compiled a static binary and they gave this minus static switch. And that's, again, what we do in Go these days. And this is why a Go Dockerfile can look like this. It's the shortest possible Dockerfile. Well, start from scratch, because you don't need anything, and then copy the binary and then run the binary. And that's great. That's what we like, because if we go from a monolith to a microservices architecture, and we replace one monolith with 117 microservices, or I just recently read Uber is running 4,000, then all this overhead is counting, because then you would have like 4,000 times the overhead, and you want to have containers that are as small as possible. So Go is one way to go. Now, if you're really critical, you could say, this is kind of cheating because you didn't build the binary in the container. You just copy it in, and everyone can do this. True, but it's also a solution for building the binary. Actually, what you can do is do this multi-stage Docker build. In the first stage, we build the binary. We can't start from scratch for the first stage. We need the Go environment, the Go lang. We build the binary, and then we copy it in the second part of this multi-stage Dockerfile. We copy the binary. We copy the binary into the image. And the second part is starting from scratch, and this from 0 says copy over the build artifact. So that's a very efficient way of building containers, because Docker is a very suitable language for doing this. How about Java? Who's doing Java? Wow, cool. Do you guys remember the times when we had application servers and they were running with 4 GB of heap or 8 GB of heap, And no offense if you're still using them, because I know there's plenty around. The question is, if we have such a big monolithic and then clustered application server, like 4 or 8 gigabyte of heap times 4 in a cluster, is that very suitable for such a microservices architecture? And what can we do in Java today? There is actually a lot of open source cloud native stacks around that become more and more popular. And they provide a minimal footprint for Java applications and make it optimal for running this in a container. What you see on this slide, the application server is not even in the chart. It's like to the very right of this slide. But if you use a modern framework, you get down to hundreds of megabytes. And then if you use a clever compiler, and the compiler that we see a lot in these days is GraalVM. It's a compiler for Java, written in Java. It's replacing the JIT, the C2 just-in-time compiler, in a more modern way. And what it does is it does aggressive code, it does code elimination wherever possible. It does aggressive advanced in-time compilation. So it's not the JIT, the just-in-time compilation that is looking for the hotspots, that is generating statistics, where your program is running for a long time without being optimized. Then you gather the statistics, and then if you have the statistics, you know the right places where to optimize. This Graal project does the opposite. It optimizes advance of time, and it will then generate a binary. So at the end, you can run a binary. It also generates you a Dockerfile and the command to run the Dockerfile. So you basically run shift, return, whatever you define in your Visual Studio Code. And you run the Dockerfile, you have the container, and then it also spits out the YAML file for deploying this on Kubernetes. So at the end, you need a kubectl apply -f, and you have your Java code running. The interesting thing is this can be compiled down to a native binary. So at the end, you're running a native binary with all the benefits that I already told you for the Go case. Now, I built one. It was, well, you see the timestamp. That was mid of last week. It's a small to-do application, and it was starting up in 0.007 seconds. That's a Java application. Isn't that amazing? So that's the magic number, 0.007 seconds for starting up a Java application. And now think back at the times when we booted our application servers, and it took like 2 or 3 minutes, depending on how many deployments or how much stuff you had deployed on those instances. So that's really amazing time. There's something else I want to mention, because it's a nice contrast. It's not really container technology, but it's something that we built, and we open sourced it. It's called Firecracker. It's a micro VM. So it's a VM that needs like 5 megabyte of RAM overhead if you start it up. It needs 125 milliseconds to start up, and you could start 5 of them per second per single core that you have on your machine. That means it should be like 180 if you do that on a 36-core machine. You could start 180 of these micro VMs and on a 36-core machine. Now, you're all very quiet, very polite people, but you should be super excited, because this is amazing technology. I guess a lot of you think, well, this is what my Docker container does. No, I've been doing this on stage, telling people, look, this is how Docker scales. You start a container, you build a small shell script that does a loop, you start up 100 containers, and you find out it will take like maybe 200 milliseconds to start a small Go binary in a container. And so every 200 milliseconds, you could start such a Docker container. But guys, this is not a Docker container. This is not the C group restricted, namespace isolated process that is running in the Linux that already exists. This is a real VM. In 125 milliseconds, we boot a Linux kernel, and it's there. So all these C group things, you probably wondered why I talk about the limitations of C groups and namespaces. All these issues are gone. This is real VM. No, this is different technology. We use it today for AWS Lambda functions. We also use it for Fargate, if you want to run your containers in Fargate, and I will come to this. And we're talking to a lot of open source projects where they say, you know, wouldn't it make sense to run a Kubernetes pod in a more isolated environment, to have more isolation, let's say, from different users using one Kubernetes cluster. So Firecracker is an amazing technology. Keep an eye on this. Let's talk about container orchestration. And I already told you, I already kind of pleaded guilty for telling people, look, this is how Docker scales, and what we do is we start a container, and we do this in a loop, and we tell people, look, on my laptop, I can run 100 Docker containers. Isn't that amazing? Never trust those people, never trust those presenters. If they have one laptop, and they work on localhost, and they run their shell scripts. That's not what you need. No, that's not what you need in production. What you need is something like this. You say, I need 10 instances. I kind of know I need 10 instances, so please start those 10 instances, but make sure they're highly available, spread them across availability zones, and connect them to the load balancer. That's what you really need. The shell script with 100 iterations is like gimmicks. No, that's not the thing. So let's talk about ECS, the Elastic Container Service. That's probably the easiest way of getting started with containers in production. And I know there's a lot of people sitting here that think like, why is he not talking about Kubernetes? I'm a big fan of Kubernetes, but if you want to get started with containers today, it's ECS. That's the easiest way to get started with containers. Reasons are, number one, it's integrated perfectly with the rest of the AWS environment. It scales to clusters of any size. We have really super large clusters from customers running in our cloud. And you get service integration like load balancer on a container level. So it's the perfect thing to get started with containers, well, in the cloud on an enterprise level. In ECS, some of you already might know, there is 2 different modes. You can go for the EC2 mode. This is where you bring your own worker nodes. And then there is this Fargate mode. And the Fargate mode is the interesting one. It's the serverless mode. This is where you don't have to bring your worker nodes. We provision the worker nodes. You tell us what container you want to run, and you give us a task definition at the end. And the task definition specifies what container you want to run. I'll show you a few more details. So the big difference is, do you want to manage infrastructure? Maybe for some reasons, because you want special worker nodes, you can go for EC2. And then we have this Fargate mode where you don't need to manage infrastructure. You just spin up your containers. You tell us the resources they need. And basically, to tell us those resources, what you do is you create such a task definition. And this task definition, it has like 2 sections. One is the task level, where you can specify resources on a task level. You can say the whole task should not use more than that many CPUs, or the whole task should not use more than that much memory. Or you can specify on a container level as well. And obviously, if you specify the container image, it's a container level. If you have resource settings for a particular container, it would also be on the container level. With this task definition, we can run a task for you. We can run your container in a task. You are in control of the placement strategy, the IP ranges, the security groups. All this is what you can specify, and we run the task for you with those resource settings that you configured. So this is the customer view. What really happened is a little bit more complicated, in depth. So what we do is we provision such an elastic networking interface, an ENI. We call it ENI. This ENI gets a private IP address. With the ENI and the private IP address, we can connect to the Fargate task. Then your Fargate task has a private IP address. And then, if you are in a public subnet, and if you want a public IP address, we can also give you a public IP address. So this is what happens under the hood if you give us a task definition, if you want us to run a task in Fargate. Now, a lot of people say, OK, but then if you really talk about production, about production environments, it's not only that we click this together in the GUI. That's not the idea. So what you need is some way to provision this infrastructure in a repeatable way, in an efficient way. And often the answer is, obviously, infrastructure as code. There's one way to do it. It's to write CloudFormation. And writing CloudFormation is writing YAML files. It's a bit like what I told you, with these Java frameworks where the YAML file is generated. there's not that many people that love to write YAML files. This is also always a good way to get around writing those YAML files. And there is one, and this way is called CDK Cloud Development Kit. And in this CDK, what you can do is you can define cloud architectures in a native programming language, meaning Python or meaning TypeScript. And then we take this native programming language and we generate the CloudFormation, the YAML files that you probably don't want to write by hand for you. And we have constructs, like you see them here, constructs for creating a SQSQ, a Lambda function, an S3 bucket, and so on. And you can take those constructs and combine them and generate your infrastructure, put them in a stack, and the whole thing is an application, and then you run the application. Now, I'm not a big expert in CloudFormation, I have to confess. I always kind of struggle to write hundreds of lines of YAML files, but I hacked together this in just like, I think 45 minutes it took me. And I'm also not a big expert in JavaScript, I need to confess, and this is TypeScript, so I'm kind of proud of what I did. If you look at this, it's declarative. We use these constructs like clusters or tasks. And if you see like what is it, line number 12, the VPC that is generated here. If you generate such a VPC, if you give us this line of code, what we do is we generate a VPC, it spans all the regions that you have, like it goes across 3 regions. We divide the CIDR range for your IP addresses. We create public and private subnets in those availability zones, and they have, like the public ones, they have an internet gateway, and the private ones, they have a NAT gateway. So if you know how to do this manually, you're kind of ready to get certified with this AWS certification solution architecture associate. This is what you need to be able to do to pass the certification, and we do exactly the same for you with this single line with this, what is it, ec2.vpc. So it's very, very efficient. And apart from those basic constructs that we have, well, that's the thing I was just talking about. Apart from those basic constructs that we have, we also have patterns. So people thought about this and said, yeah, it's okay, you know, we need clusters and we need VPCs, but very often what I want to do is I want to run a Fargate task with a load balancer. And this is why we have those patterns. And the number of patterns is increasing. It's open source, it's on GitHub. You can check it out. And if you run this little bit of TypeScript, and I was counting it, it's like 568 lines of YAML file of CloudFormation. I would not be the person, to be honest, to write the YAML file, but it was very easy for me to write this TypeScript, even though I'm not a JavaScript programmer. So this is very, very efficient stuff. Again, we call it declarative, and it's declarative in a sense that if you configure if you write down 2 lines for VPCs, you want us to generate 2 VPCs, we will generate 2 VPCs. If you run the same thing again, but you remove the second line for the second VPC, guess what happens? It will remove the existing VPC. So it knows about the state. It wants to achieve the state that you describe. That means by not putting the second line, it will remove the second VPC if you have already provisioned it. That's the important thing to understand. This is why we call it declarative, and this is also why it's not like the typical program that you see that is just executed. So it goes back to CloudFormation, and then CloudFormation knows what to do. Maybe you heard about the AWS Hero program. We have some AWS Heroes, and some of them are specialized in containers, others are specialized in serverless. We have community heroes that run a lot of meetups. And one of the container heroes is based in Munich. His name is Philip. That's him. He has a great blog where he kind of combined his experiences in creating advanced CDK scripts. All those slides, they're already on speaker deck, so you can take photos if you like, but it's not really necessary. On speaker deck, you get the slides, you get the URL. If you want to learn more about the CDK, that's a good place to go. Right, and then we have Kubernetes. There's a lot of people out there that have great Kubernetes knowledge from running Kubernetes on premises, from learning about Kubernetes using Minikube. So a lot of people asked us about Kubernetes at a time when we had ECS already up and running and nicely integrated with the rest of the AWS services. And imagine that. Imagine you're a cloud provider, as we are. You have a service that is, well, perfectly good, no? That does what people want to do. And then the customer come and say, we want to have Kubernetes, no? And that's actually what they told us. They said, could you run Kubernetes for us? So their experience was, obviously, they can try it themselves. They can use EC2 instances, install Kubernetes, and, well, try to operate Kubernetes on a infrastructure as code level. And most of them were not really happy. They understood that this is just too much operational knowledge that you need. And you need this knowledge like, 24 hours a day, every day in the year. And it's like super difficult to get skilled people, to operate such a cluster. It's not just setting it up. It's far away from running Minikube on a laptop. Never listen to those people if it's about production issues. It's also far away from setting it up in a distributed way across EC2 instances once. That's easy, no? But what would you do if it goes wrong? If you really have a problem, if there's some weird things happening, how many people do you have that you could call and you have some confidence that they could help you to fix the problem? And you should have them 24 hours a day. So this is typically why people tell us we want Kubernetes, because we have a strong Kubernetes experience already. We have it on premises. We want to use it in the AWS cloud. But they also tell us we don't want to operate it. Could you operate it? Could you run Kubernetes for us? And usually in the same sentence, they also say, but don't change it. Don't put bells and whistles. Don't make it incompatible. Just run it for us. And that's what we do. We run Kubernetes for you. We run the backplane, the control plane, which contains the API server. It actually contains the etcd, which has the state. And this is what makes it difficult. Whenever you have state in an architecture, you have to make sure you don't lose the state. So we replicate the etcd process across availability zones. We snapshot it at a regular interval. If something goes wrong, we restore it. We give it provisioned IOPS to make sure it's efficient, it's fast enough. And all this we do for you. And you see nothing about this. All you get from us is a fully qualified domain name. It's this mycluster.eks, this case. And then you bring your worker nodes. You connect the worker nodes to the backplane, to the control plane, and you run your Kubernetes cluster. Bringing the worker nodes has the advantage that you can bring bare metal worker nodes if you want. You can bring worker nodes with GPUs. A lot of people say, why would you bring GPU worker nodes? There is a lot of machine learning workloads running these days on Kubernetes, also in the Amazon cloud. You can use spot instances. A colleague of mine loves to say, people often come for the managed control plane to AWS, and then they stay for the spot instances. Those spot instances are those instances, I guess you know, where you bid for the price, and it gives you like a price reduction that is typically like 80%. So people love those spot instances, and they are used a lot. And then, because it's standard Kubernetes, you can use your favorite tools. You can come with kubectl. You can come with K9s. It's another one that is very favorite. All those open source tools, they will work. There's one tool. It's been around for a while. It's open source. And it used to be my favorite tool for the very beginning, because all the complicated way that you need to set up a Kubernetes cluster in production is very much simplified. So basically what you need to do is you say, EKS control, create cluster. The name is obsolete. If you don't put a name, it goes the Docker way. It will create a funny name for you. My cluster is called, I have one running here, but I don't have the time to show you. It's called Beautiful Paintings, and it picked the name itself because I didn't specify it. And then if you want to connect it with the AppMesh, you also say ---- AppMesh, and then you have it. So that's the easiest way to create a Kubernetes cluster. People were hesitating to use this tool and said, but it's not AWS, it's open source. Well, that's one of the benefits of using Kubernetes open source. Now you can pick the best tools. And now we also wrote a blog posting recently and kind of explained this is our official recommendation now. Go and use EKS control if you don't want to do it manually. You can always do it manually. That's not the point. Right. And this brings me to what you can do on top of Kubernetes. On top of Kubernetes, if you want to get things done like connection retries, Or you want to do something that, I think Netflix became very popular with this, like a circuit breaker pattern if something goes wrong downstream. What if you want to do something like a bit of cars engineering? You heard some cars engineering talk, and you think like, how would my clients react, like the technical clients, not your customers? How would my clients react if there is a latency in the response? All these things are difficult to implement on an application level. You should never implement them on an application level. But how do you get these things done? Well, one solution is this. You take a library, and there are these libraries from Netflix, from this open source software center, where they put in the circuit breaker and all these things, and you use those libraries. And they contain this logic, this layer 7 networking logic. Good idea or bad idea? It's working. The disadvantage of this approach is it's a library, it's language specific, you have to change your code to make use of the library. And tell your boss you need to change your source code to make it run in the cloud, it's a bit weird. The question is, how else could you do it? And the answer is, well, go and use a service mesh. In a service mesh, we kind of extract the same functionality. So it's a shift in functionality, and we put it in proxy. The proxy is running in the same pod as the container. It's actually sharing the same network namespace. This is why we talked about it now. Because it's sharing the same network namespace, it can work as a proxy if, like, the microservice on the left-hand side wants to talk to the one on the right-hand side. It goes to the first proxy, goes to the second proxy, and then talks to the microservice. This is why those proxies are super interesting, and you can get a lot of telemetry data from these proxies. So this is open source. The most commonly used service mesh is definitely Istio and Envoy. Envoy is the proxy that I was just talking about. And go and use it on EKS. This could be the end of the talk, but I have a few minutes left. This is why it's not the end of the talk. If you want, run this on EKS. But a lot of people said, we want more. We don't want to run only Istio and Envoy on EKS. What we want is a service mesh that is working across all the compute that we give you. What's all the compute? Well, all the compute is ECS. It's ECS with Fargate. It's EKS. It's actually still EC2. There's a lot of EC2 around and monoliths running on EC2. So EC2 included and self-managed Kubernetes on EC2. And we built that. It's called AppMesh. Good news is it's based on the Envoy proxy. So the same Envoy proxy that you can use in open source projects, Istio plus Envoy. We use the same proxy. We're not using Istio because, well, we had to make it work across all those compute services, and that's why we built our own AppMesh. It's called AppMesh. It's a service mesh. And you can install it with one single line for demo purposes. It's Helm install. And it installs the AppMesh and the Envoy proxy that we later inject as a sidecar. It also installs the Xray daemon that we use internally for AWS Xray. And it installs the statsd Prometheus exporter, so you can use it for Grafana. A lot of people think it's either the CNCF way, you use all those, Kiali, Jaeger, Grafana, whatever tools, or it's the AWS way only. And we kind of built this demonstration, this deployment to show you can do both. Any second, you can decide what you like most. So this contains a lot. It contains more than what you want to use in production. And that's the interesting thing, to understand how to make it work. We create a demo application, and this demo application is living in a namespace. And the second yellow thing, that's the important one. And then we tag, we label the namespace, and we say, well, injection enabled. Technically, it's using a mutating webhook admission controller, which basically says, if you run a pod in a namespace with this tag, with this label, then inject the other proxy, this additional proxy that brings you all the service mesh magic. Now, I did that. I made it work for you. And this is the statsd Grafana exporter. It gives you a predefined Grafana dashboard. You get an overview. I'm most proud of this number that you see here. It's 16 weeks, which is like, what is it, 4 months, 5 months almost? So it's not Minikube running on a laptop. It's something running all the time and never going down. This is why it's EKS, it's Kubernetes on an enterprise level. You see the top 5 services. You see the top 5 services by error. You see connections, upstream failures, all the things that we predefined that you could define yourself in a Grafana dashboard. So that's the open source way, that's the CNCF way that you're ready to go any time now. And this is the other side, that's Xray. This is where we take the data, the telemetry data, and look at it using AWS Xray. I hope it's starting. Yeah. So we have a service map. We can compute which microservice is calling which other microservice. Imagine your Uber, you have 4,000 of them. You need to understand what's the pattern, which service is calling which service. The box on the right-hand side, it shows you the percentiles like the P50 and the top 4% are this 50 milliseconds. Then we get traces like the spans that you get in a Jaeger display. So it's 40 milliseconds for the load generator that is calling an Nginx backend, and the Nginx backend needs like 24 milliseconds. And then we can do more analytics based on this data and narrow it down and so on. I don't want to go into details here. All this is public. If you want us to do more, if you want us to do different things, talk to us. You can open a GitHub issue and let us know what is missing in your opinion. So the whole roadmap for all the container products, ECS, EKS, AppMesh, ECR, the container registry, it's all public. Let us know if you're missing stuff. With this, I want to hand over to Brian. And Brian Bodini from Richmond will tell you about his experience running Kubernetes. And well, I've seen the presentation already. He's also talking about teams. And his team is doing something that we do internally at Amazon. We have a lot of 2-pizza teams. Now, Brian's teams are eating more, I think, and I'm curious to find out why. So welcome on stage, Brian.
Hello, everyone. I am very excited to be here today to share our journey in Kubernetes. OK. So I started as a developer, but after a while, I moved to operations and architecture. I passed to the other side, and a new world has opened for me. I'm working since 1 year with Kubernetes, and since 2 years, I am working with cloud services. I worked in banking and insurance industries, always in Switzerland. And 4 years ago, I moved to Richmond in the luxury domain. I am based in Geneva, but I am a lot of time in Shanghai, in China. What is this journey all about? This is a web product I am going to share with you with a global user base: US, Africa, South America, Japan, Asia, all over the world. And we had many challenges in many different domains. We have customer satisfactions, which is our first priority. And what customer wants for web application is to have fast, responsive, but it is not only about being fast. Today, when you navigate a website, you navigate most of the time with an iPhone or a device, mobile device. Browser from desktop are not the only one. Time to market. We needed to build something which is adapt to what the business and the customer want. So we needed to be fast, to iterate very, very fast. But also, when you go to production, you have figures, you have a forecast, but they are not always accurate. We didn't know at launch how many users would use the platform. And of course, we had also security, compliance, and last but not least, cost optimization. This that you see here is the high-level architecture. So we start with the customers, which are accessing over the internet with different devices. And since our customers are dispersed all across the world, we have used a content delivery network, CDN, to achieve faster response time. And then we have used the Amazon S3, simple storage service, to store static files. As you are guessing, when you use a mobile device, you have a different resolution. And with different resolution, you have different images with different format. And we have stored this static asset in S3 to avoid a round trip to the applications. Then we descend down, and we have a load balancer to spread the load across multiple instances. What you see there are multiple autoscaling groups, because the Kubernetes workers are managed by us, by the customer, while Amazon is managing the masters with Amazon Elastic Container Service for Kubernetes. But then it is not only this. We have used Amazon SQS, Simple Queue Service, for different use cases. Integration with on-premises or legacy applications, events processing, and also batch processing. More on this later. And then for integration with on-premises applications, we had used Direct Connect. And last but not least, at the bottom, we have used two different types of databases. Aurora for relational data, and also Elasticache, Redis, for caching purposes. As I mentioned before, we have used 3 pizza teams. We have discovered that the cloud has freed the appetite also for our developers, along with many interesting use cases. The team is composed by 8 developers, some front-end, some back-ends, 1 quality assurance engineer or testing engineer. This is what other companies use. He was responsible to make a test and automated test. 1 lead architect for the integration across multiple services. 1 solution architect that was doing also automation engineer, so working with Terraform, CloudFormation, managing the cloud infrastructure and the Kubernetes, developing pipelines and so forth. 1 product owner, which is responsible for the business side, business analyst, and 1 agile coach. This was our first project doing in this way. Now I'm going to introduce you our values, the values of these teams. Customer satisfaction and time to market. I decided to put them in the same slide because these two, for me, are like a marriage couple. You can't have a satisfied customer if you release your software 1 time per year. And how have we achieved these goals? Fast provisioning and low operation overhead with managed services. We have provisioned our resources in a matter of hours. But how we have achieved this? We have achieved this with automation, with templates. CloudFormation first, and then we have used Terraform. And I have to say, before doing a cloud, I was responsible for operations, setting up virtual machines, setting up services, databases. And I have to say, the cloud has removed me all this overhead. While before doing firewall requests and so forth, it took weeks. With templates and automation, I have achieved this in a very short time. And this has helped the project a lot. But it's not only about being fast. It is also about repeatability and consistencies. Many times you will discover doing any cloud project, especially at the beginning, you are doing a lot of provision and destroy. And later on, you have to do changes across development environment, integration environment, pre-production, and production. So it is very important to have something which is repeatable and consistent across environment. Otherwise, you risk to go to production with features missing, different version, etc., etc. And Docker, what has allowed the developers team, which was new to Docker, is to have a seamless experience from their local workstation to production. And the developers, after some ramp-up, they've also started to use Docker for own local testing in their virtual machines. What I have seen so far, the situation that we are today, Docker Compose is not anymore sufficient. So we will switch to have dynamic environments in Kubernetes. Unpredictable load. This has been our first worldwide launch across all over the world. And we have designed this project to be elastic and simple. And what we have discovered is that keeping things simple, it helps you a lot doing a production rollout. We have decided to put elastic workers in auto-scaling groups. And these Kubernetes pods, which are running in these auto-scaling groups, are stateless. They do not have data. They don't have persistent data. All the persistent data is outside of the cluster. This has allowed us to avoid a lot of headache that other people have already encountered when deploying and running database in Kubernetes time ago. And what we have used as caching is CDN and Amazon Elastic Cache to store and cache frequent operations. Security. Security is very important as well. With cloud providers, with Amazon, you can do encryption, rest, and in transit very easily with one click. But I am not fond of the expression one click, because security comes also at provisioning time. It is very important to have a versioning tool like Git, which you store and audit all the changes, what has been changed, when has been changed, who has been requested the change. So when things happen, you know already what happens and where. When you use Amazon services, managed services, you have automated certificate rotation. And about the Airbox access control, everything is managed with IAM, so one place. You do not have any more accounts that are stored in multiple places. Cost optimization, last but not least, which is a very important topic. We have decided to go with a mixed infrastructure between spot instances and on-demand instances that we are going to change to reserved instance. And this, what has allowed us, is to provision more resources and to evaluate how much resources we needed at a certain time. What we have discovered is that later on, when we developed our product, we had different use cases. Sometimes we had to do batch processing. So when it comes to batch, we have separated the batch workloads, the batch pods, from the application business user-facing front ends. This has allowed us to use spot instances so that we provision our workloads and use as much as possible resources without impacting the web application. But also to keep the cost low, we have used CloudWatch and Lambda to have an automatic shutdown, a scheduled shutdown at night and in weekends for the services like development and integration environment because nobody is working. And right now we are working to evaluate how many purchase reserved instance we are going to buy to keep cost under control. Timeline. As you can see, the project started 1.5 years ago, in January 2018. And there we had the project inception. We had discussed with the business, security, and so forth. And in March, we have started with Amazon Container Service to have a return of experience for developers to try and test the deployment options with Docker, etc. But later on, in July 2018, we have provisioned ourselves or Kubernetes because there was a decision to have a uniform cloud orchestration approach. And then we have started to see how much difficult it was to manage and harden the Kubernetes masters and manage etcd. In December 2018, Amazon released Amazon EKS in Frankfurt. And in January, 1 month after, we have switched to Amazon EKS. And at last, in May 2019, we have done the go live. Outcome of this journey. Customers were satisfied because the application was fast and responsive. But what I like a lot is that we have a scalable infrastructure according to the workload we have. And this requires a lot of work and a very good monitoring team that I sincerely thanks. And last but not least, we had a team ownership from inception to production. This allowed us to have a sense of responsibility in the team, because when the team was called at night, in the morning, I assure you, the first thing that they have done is looked at what went wrong post-mortem and apply the necessary solution to not be called the night after. And then we had a faster time to market because we can iterate very, very fast. We can provision resources on the fly. And this has allowed us to have a reusable infrastructure for other projects which can leverage on the experience of what this team has achieved. And of course, infrastructure modules are also included. What next? Right now, we are evaluating to switch the event processing from SQS to Amazon Kafka. We are going to see what the team will decide. And thank you very much for your attention. If you have any questions, you can reach me on either on LinkedIn, Twitter, or by voice. I am here at the conference, so feel free to have a chat with me. Thank you very much.
Thanks very much, Brian. Thank you for all of you being here. There's a short summary. We believe the cloud is the best way, the best place to run your containers. Architect wisely, choose whatever is best for you, serverless, ECS, EKS, or even EC2. Running Kubernetes is hard. Think about a managed Kubernetes service, and go and try and see if AppMesh is good for you. It's free. You can try it. You only pay for the resources that you use. With this, I want to say thank you to all of you for being here. That's the only picture where you should take the only slide where you should take a picture. It has the contact details. The slides are on speaker deck already, so feel free to download them. Contact me on Twitter. We'll be around for questions. We don't run away. Just talk to us. Thanks again, and have a good conference.